Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. Today, folks, we have Max Kanat-Alexander presenting Code Simplicity, the Science of Software Design. Max is the author of the best-selling O'Reilly book, Code Simplicity, the Fundamentals of Software. We're so excited to have Max with us today to present this webcast for you all. As we get started here, folks, we'd like you to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Max. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Max, please preface them with a capital letter Q so we know that they're for him and we can make sure he sees them for Q&A. You can also open, move, and resize any of the other widgets. If you would like to tweet from the Twitter widget today, you may need to give it permission to access your account. It will automatically append the event's hashtag to your tweet so you don't have to, and today our hashtag is Code Simplicity. If you should have any problems during the event, please take a look at the Help widget. If you continue to have problems, please post it in the chat room and one of our staff will help you right away. For choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know, we are recording today's webcast and we'll have an archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Max for his presentation. Hello, Max.
Hello, Yasmina. Thank you so much. All right, so this is, as Yasmina said, Code Simplicity, the Science of Software Design. And I guess the first question is, who am I? Well, I am a person. You can't see me, but I promise you I'm real. I refactored Bugzilla, which is a bug tracking system, from sort of a very difficult to work with code base to what was eventually a much nicer code base over a period of many years. And during this process, I learned a lot of things. In addition to having a lot of other experience in software development, I've actually been developing software for something like 17 years now. I wrote a book for O'Reilly called Code Simplicity, and I'm also the author of a blog at codesimplicity.com. And presently, my day job is that I am a software engineer at Google. I actually work on YouTube in particular. So what we're going to talk about today is software. In particular, we're going to talk about software development and software design. Now, one of the great things about software development is that everything is perfect all the time, and everybody writes great software, and it's all really easy to work with. And of course, the whole field of software is, well, it's a mess. So obviously, everybody is having this experience, almost everybody in the world is having this experience where they're like, I am dealing with this terrible piece of legacy software, and I don't know how it got this way, and why is it that every time I work on a piece of software, they all are these massive pieces of complexity, and they're all really hard to maintain, and everybody's complaining about their system that they're working on, and sometimes they're complaining to other software developers, and they're just sure that somewhere in the world there's a system that is not terrible like this, even despite being made by multiple people. But no, everybody's having this experience. So why is everybody having this experience? Well, some people might say that's just the way it is. All systems eventually become too complex. Eventually, you're going to have to rewrite everything you ever write. But that's a bit like saying all skyscrapers we ever build are going to fall down, and you're going to have to build them again. So it can't just be that that's the way it is. Well, really, a lot of what's behind this is that we are dependent upon experience to learn the great and important lessons in software engineering. But we're building with a team of people, and not everybody has all the experience necessary to be able to make all the right decisions all the time. And particularly newer developers, the newer of a developer you become, the more and more you are likely to make missteps because we are totally dependent upon experience to learn the most important things in software engineering, and you can't have had that experience yet. Even if everybody has a lot of experience, not everybody has the same experience. So some people might have learned certain principles or have gained certain lessons through their work in the industry, but maybe not everybody has, and maybe everybody's learned different things. So it's hard for everybody to come to an agreement about what design principles should be being used, and exactly how we should all maintain quality, because everybody has a different experience. And this also results in the fact that not everybody shares the same vocabulary. When you've learned something by experience instead of through reading it or some sort of verbal communication, there's no words. There's no way of talking about it with other people. As a result, it can be hard to explain why you want to do the right thing to other people, particularly to non-technical managers or to the non-technical parts of the organization. But sometimes it's hard to explain even to yourself. People are like, you're like, oh, I have this deadline, and I really feel like I should do the right thing here and write better quality code, but I can't really exactly explain why even to myself, so I'm just going to go with the deadline. So the solution to this that I am attempting to bring to the world is what I call the laws of software design. And these are basically a set of fundamental principles which, when understood, should give everybody a common vocabulary and also help everybody make decisions. Now, today I'm only going to be able to give you a whirlwind tour of these because this is not a very long presentation. I do longer presentations when I speak in person, and then, of course, I also wrote a book called Code Simplicity, and almost everything in this presentation is also in the book, but in much more detail. Okay. So I'm going to tell you a lot of things today, and a lot of them you're going to think, that was really obvious. And people tell me this. People come to me, and they're like, you told me a lot of things, but I already knew those things. And yes, I agree. A lot of the time, you already knew those things. But there's a little bit more to data or to knowledge than just having the data, right? One of the things that's important about data is that it be separated out and that you understand what is the most important data, because in the field of software engineering, there is a sea of data. There are so many opinions. There are so many methodologies. There are so many books, so many systems, so many opinions that, how do we pick out what's most important from all of that? So what we need is we need to be able to pick out the most important pieces of data, and then we need to be able to use those most important pieces of data to be able to judge other opinions or facts or proposed methodologies that people propose to us. Because, otherwise some consultant can just come into our company and be like, you should use the new foo method, and everybody's going to go, okay, because they have no way of judging whether the foo method is good or not. Or maybe somebody's going to come in with a great suggestion, and everybody's going to reject it because they have no way of knowing that that's a great suggestion. Just as an example, and to yourself, could you list the 5 most important facts about software design right now? Because that's basically what I'm going to tell you in this presentation is these are the 5 most important facts about software design. If you think about it for a second, what are the 5 most important things about software design? Not like the 100 most important things, but just 5. And then, of course, another important thing is we need to be able to communicate these ideas to each other. Because, like I said, we need to be able to have a shared vocabulary, and we need to be able to share the experience. We need to be able to tell our managers. We need to be able to discuss quality, and we need to be able to talk about our plans with each other. So with that said, let's get into it. The first quote-unquote law of software design is not really a law. It's something that I call the purpose of software. And you can think of it as our guiding principle. When I say these laws work or these laws do something, it's that they accomplish this purpose. And so the question is, what is the purpose of all software as a whole? Every single piece of software ever written. And the purpose is to help people. It's mostly important that you know that the purpose is not to help the computer. You're not writing to make the network go faster. You're making the network go faster because that helps people. And now help is both, has an objective component and a subjective component. So, sometimes what helps one person might not help another. But there is a somewhat of an objective aspect, which is it has a definition, dictionary definition, which means to make it easier for a person to do something, often to do part of the work of a person. So that's a lot of what our software is doing. And then we can break this down and say specific software has a specific purpose. And sometimes we can even say that it helps a specific group of people. For example, a piece of tax software helps accountants do taxes. People often ask me, what about malware? Well, it's funny, if you talk to the writers of viruses, very often they believe they are helping somebody do something. I remember reading an interview back in the day, I don't remember where it was, PC Magazine or somewhere, many, many years ago, where a virus writer said that they wanted to help people realize basically how dumb they were being and how insecure their systems were and how much more careful they needed to be. So there's, like I said, and like I will say about all of the things in this presentation, there's a ton more to know about this. There's a lot about how to apply it, but that's in the book. So our next law is the equation of software design. This tells us something called desirability, which is basically how desirable a change is. What we want to know, if we have a selection of changes that we could possibly make, we want to know which one of those changes we should pick or how we should prioritize those changes. Which should we do first? Which are most important? Because there's no absolute right or absolute wrong in the field of software design. There's never a black and white decision, as many people try to pretend there is. There's just basically infinite shades of gray, and you want to find the right shade of gray for your solution, for your situation. So instead of just saying something is right or wrong, you want to be able to rank a bunch of possible options. And you're never going to get to the best option because there is no best option or perfect option. So the most simple, overly simplified version of this equation says that the desirability of a change, feature, or decision is directly proportional to the value of a change, which means how much it helps people, and inversely proportional to the effort involved in making the change, which includes all of the effort that is involved, even all the bug tracking, all the talking, everything. However, this discounts the fact that software is maintained over time. So we need a more expanded version of the equation to actually be true. And it basically says that, so we break down value into the value now and the future value. And value now you can think of as the value that you get right when you release the software or right when that feature goes out or right when that change hits users. And then future value is all the value you get after that. And there's tons of examples of this, and I can explain it more, but we don't have time, and it's in the book. And then effort can be broken down into the effort of implementation, which is, once again, the effort basically up until you submit that patch or that change or until it hits users. And then effort of maintenance, which is basically the total effort of the total increase in effort required to maintain the system because you made this change. Right? Because sometimes you make a change and it makes other things harder to maintain as well. Now, anybody who has taken calculus or studied limit equations might recognize that the value now and the effort of implementation are effectively constants, and the value in the future and the effort of maintenance are functions of time. So as time goes to infinity, the constants drop away in most situations, not in all situations, but in most situations. The constants drop away, and we are left with this as the limit of the equation, which is that the desirability of any change is directly proportional to its future value versus its effort of maintenance. Like I said, there are situations in which the effort of implementation and the value now matter, but they are not. They are probably 1% or less of all changes that I've ever personally encountered. I'd be interested in doing a broader study to actually classify and find out what differentiates those types of changes. I can tell you when I see them, but I can't exactly explain to you when the effort of implementation is important straight up here in this presentation. The most important thing to learn out of this is that you want to avoid situations where the future value is outweighed by the effort of maintenance. As long as the future value is increasing at a rate faster than the effort of maintenance, you're good. You could write a system in which the effort of maintenance continuously increases, as long as the future value continuously increases and is higher always than the effort of maintenance. And what this tells us is it tells us a very important fact about software design, which is that it is more important to reduce the effort of maintenance than it is to reduce the effort of implementation. Because you reduce the effort, if you increase the effort of implementation, then that's just a constant. It doesn't matter. It's a predictable amount of work, whereas the effort of maintenance is an unpredictable amount of work which could go on forever and ever and ever. And so, of course, this is something that many of us know, but this gives us a pretty good, more mathematical grounding and emphasis on that it is important and how to explain it to others. Like I said, of course, however, the future is full of unforeseeable consequences. There's a lot of future in the future. And there's a lot about that future that we can't predict. And the farther away it gets into the future, the harder it is to predict what's going to happen. Software pretty universally has long timelines. A short project is several months. Most projects are maintained over several years, even if you only expect them to be maintained over several weeks or several months. So as a result, most of the consequences of our software design decisions are consequences that we can't know. And attempting to predict them is a lie and a waste of time. In fact, you're better off not attempting to predict the specifics of the long-term future or the long-term consequences of your design decisions at all. One of the greatest mistakes that programmers make is attempting to do this when they, in fact, cannot actually know those things. They say things like, we will never have to reuse this code. Well, you might or you might not. You don't know. You don't know that. You shouldn't make your design decisions based on that prediction. They say, we might need to handle 5 other types of input to this function or method. You might, or you might not. Why would you make a design decision based on you might need to? I mean, sometimes you do have to make assumptions. A lot of the time you think, okay, right now this application is only going to be in English, but someday we're going to want to internationalize it, and it's easier, much easier to do that, to set that up as we go, or to make that decision at the beginning than it is to make it later. But you have to be aware that you're making an assumption. You have to not put a tremendous amount of effort. Like if this adds a tremendous amount of complexity or additional effort to your system, then you want to find a way to reduce that effort or reduce that complexity if you're going to be working based on an assumption. And ideally, you should be making this decision based on a ton of past experience with other systems, or talk to somebody who has a ton of past experience with other systems and ask them. The rule that I propose to avoid having this problem of making assumptions and then basically finding out that they're always wrong is don't try to make specific predictions about the future. Instead, make your design decisions based on presently known information, so the things that you know right now for sure, rules, so the rules, sort of like the rules that you know about software design that are sort of like these broadly known rules, and laws, because laws are basically by their definition things that are always true. You don't have to guess whether or not a law will continue to be true in the future, and that's basically what law means to a large degree in this context. Now, there's sort of a contradiction here that I've told you, right? So I've told you the effort of maintenance and the future value are really important, but then I've told you don't think about the future. Don't predict the future. So This sounds like a contradiction, but in reality, it's not a contradiction. There's a difference between designing right now in a way that is guaranteed to reduce future maintenance. Now, that's what I'm telling you to do. I'm telling you, do good design right now in a way that you know, without having to predict anything about the future, makes maintenance easier in the future. And then 2, attempting to predict something specific about the future, like tomorrow I'm going to be attacked by a horde of babies. You don't know if you're going to be attacked by a horde of babies unless, maybe somebody sent you an invitation to being attacked by a horde of babies, and then you know. But otherwise, you don't know, so don't make that specific prediction. Just do good design in the present, using present information, using rules and laws. The next is the law of change. If you want, you can break this down to entropy. One of the things that I'm not doing today is I'm not going through the proofs of these. I'm not talking about the research. I'm not talking about the experiments. This is basically just the conclusions, because I don't have time to get into any of that other stuff today. Also, surprisingly, a lot of people are not interested in those things. I had a lot of that information in earlier test versions of the books, and readers were bored. They were very bored. They found it pedantic. So I mostly just present my conclusions, and then if you want to know a little bit more about how I came to these, I'm happy to discuss those with you in person, but not in groups, because most of the people in the group tend to not care, surprisingly. So let's get to the law of change. So the law of change says the longer your program exists, the more probable it is that any piece of it will have to change. It's pretty straightforward. If you have a system, and you have various pieces of it, you look over those pieces of it, and you look at how often those pieces change. And you can see that even you write something and you're like, this piece will never change, and then 10 years later it's totally different, right? But it's a probability. It's a probability. You don't know exactly which piece is going to change, but you can guess that on the aggregate there's going to be a fairly steady rate of change, as long as you want your system to continue to help people. One of the important facts to take out of it here is that it's impossible to make a system that doesn't change but continues to help people just as well as it does now. That is, there's a sort of a decay to helpfulness, and you have to continuously put helpfulness back into the system. That's a really oversimplistic way of looking at it. What's actually going on is, there's changes in the environment around you, and you need to change to cope with the changes in the environment around you. But a simple way to think of it is that there's helpfulness entropy. Now, there's a couple of dangers that developers get into when they try to cope with this, because a lot of people, once you've worked on a system for a little while, you realize, okay, things change in ways that I can't predict. But the rate of change is fairly steady, and you can see that. But it's very easy to misstep. And I would like the slide to change. Okay, there we go. And in particular, there's 3 major mistakes that developers make when they are trying to design systems that cope with change. The first is writing code that isn't needed. People think, I think that something will be needed in the future, and so I'm going to write it now. There's a principle from extreme programming called you ain't gonna need it. It's not actually that you ain't gonna need it, it's that you don't know exactly how that needs to be structured yet. Even if you do need it in the future, like you need, I don't know, you think you're going to need to parse some new kind of input, right? And then you get to the actual future and you discover that the input has changed formats, right? Like there was some other team that was providing you this input, and they changed formats, and so you have to write a whole new parser anyway. So you wasted your time, writing a parser in advance. And so it's usually a mistake to write code that you don't need right now. The next mistake is not making the code easy to change. Now, this usually comes about by people thinking, okay, I can make a system that will never need to change. I can make a system that anticipates all future needs and all future requirements, or a system that, or one of those sort of big design up front or waterfall systems where somebody's written a 200-page spec and then and then they'd like, okay, go write the whole spec with 1,000 features all right now. And then you build up this whole system, and then by the time you get it out 2 years later, it's not the system that anybody needs or wants, but it's so monolithic and so enormous that you can't change it. That's a mistake. You can't do it. That's basically a prediction of the future about things you can't know. And then the last flaw is being too generic. This is a flaw I see mostly in mid-level to high-level software developers. They have learned that and it's particularly bad the very first time anybody ever picks up a book on software design patterns. They think software design patterns, these are great. I'm going to use them for everything, and I'm going to make everything super generic, and I'm going to be like super defensive in all of my programming. And sometimes that's right, but it's mostly right when you can see in present time that being generic removes code duplication, as opposed to, I think I'm going to need this component to do other things in the future, so I'm going to make it generic enough to do all possible things. That's a bad idea. I know that many people have been taught otherwise. Many people have been taught, oh, the thing to do is to make things generic before they need to be generic, so then when you get to the future, you've already got code that does that, but it never works out that way. I remember one developer told me a story about, they did this 100,000 line of code project, and they added all of these points to be generic, and it turned out that all of the points where they needed genericness were the points that they didn't add it, and all the points that they didn't need it were the points that they did add it, and so they just had a system that was complex and hard to maintain. All right, so the next law, now this one is one of the most well-known ones, but it's important to point it out as a law and as a thing that you can use to know what's going to happen in the future, and a thing that you can use to base fundamental design decisions on, and that you can use to judge development methodologies with. So defects are bad because they don't help people. They break things. That's, like I said, I gave you the purpose up front to explain to you why all these laws exist, and this one exists because defects are bad. And they are basically the opposite of helping people. They prevent you from helping people. That could almost define a defect. There's a better definition than that, but we're not going to do it. The law states that the chance of introducing a defect into your system is proportional to the size of the changes you make to it. There are no perfect programmers. Studies tend to show that very good programmers will introduce one bug for approximately every 100 lines of code that they write. And amazing programmers working in like super strict ideal situations, like like they're working on a heart monitor and they have like these insane QA processes and they have these extremely strict guidelines and everything has to be totally tested, and they're writing on like this real-time system where they can know every single thing about the timing of everything that happens, and everything is totally deterministic. In that situation, usually you get one bug for every 1,000 lines of code. So that's sort of the ni plus ultra, the ultimate possible like minimum of defect introduction. And that's not going to happen on your projects probably. Basically, and so ultimately what this tells us is we take all of the laws that we've looked at so far, and it tells us that the best design is the one that allows for the most change in the environment, because things are going to change, with the least change in the software. Now, once again, some people are tempted to accomplish this by being too generic, but the problem is that that doesn't work. It doesn't actually prevent future change, because it turns out your genericness is wrong. Your genericness made things more complex and so required more change in the future, because you had a lot more code to change, because generic code is usually more voluminous. There's more code than specific code. So in reality, what accomplishes this the best is usually strictly designing with present time information and for the present and for your present requirements, without excluding the knowledge or the fact that you're going to have changes in the future. So you want a good design. You want to eliminate code duplication. You want things to be sensible, and we're going to get into this with next law a little bit more. But you don't want to do it by predicting the future. You want to do it by being strict about the present. All right, and now we come to our sort of our keystone, our most important law. This is only one slide in this presentation, but it is about half the book. And it's a law of simplicity, and it states that the ease of maintenance of any piece of software is proportional to the simplicity of its individual pieces. And I want to point out that this is the primary determiner of maintenance difficulty. Yeah. In fact, I'm not aware of any other significant determiner of maintenance difficulty. So it's not just that there's a correlation here, but that this is pretty much it. And if you've never worked on a system that's been well designed or a system that's simple, it's hard to believe this. But as you bring simplicity to a system, it becomes more and more and more apparent. Sometimes if a system is very complex to start off with, it takes a long time to see the benefits from that. And so it's hard to believe at first. And a long time, I mean, like it can be 2 or 3 years. But eventually you do start to see the really rather remarkable payoffs of simplicity. Now, what do we mean by simplicity? Well, we mean a lot of things. But a fairly good way of looking at it is how easily can a particular piece of the system be correctly understood and used by others. If you're looking at a file, can you understand that file? Can you understand its purpose? Can you understand the code? Can you understand the documentation? And is it immediately obvious how to use it correctly? That's usually a big problem, and that tends to lead to a lot of defects in software, is people writing things that are hard to use correctly, which is ultimately the responsibility of the original author and not the responsibility as much of the user, because the original author had the opportunity to make the software easy to use correctly and did not. And I granted that is hard, but that doesn't absolve anybody of responsibility. And one of the most important things about this law is that it tells us how to reduce the effort of maintenance without predicting the future. This is basically how we know in present time, like, okay, so and I use this all the time. So somebody sends me, a patch to review for our code review process, and I accept it or reject it, usually based on simplicity or complexity. And sometimes people ask me, then why? Like, this is an important feature, and I agree that it could be simpler, but like, why should it? Like, why does that really matter right now? This is just one tiny patch. Yeah, but that's what that person always says. Every time they submit something, they say, oh, but the complexity here is acceptable. And then eventually it grows beyond bound because you didn't stop at every single place that you could. And so I tell people, because, this is how we make maintainable software. I can't understand this. And so it's not maintainable. That's a pretty good rule of thumb. Is this about as easy to understand as, like, the average, like, novel that I read? Can I read this code like a book? Does it all immediately make sense? Okay, good. It can go in. It does not pass that standard, then no, we need to talk about it. And sometimes I don't know immediately what needs to be done about it, but I do know that something needs to be fixed. You don't, just because you see complex code doesn't mean you know the answer to how it should be simpler. But a lot of the time, discussions or waiting or walking around or waiting for that epiphany that happens in the morning in the shower or when you're taking a walk can solve the problem. But the solution is not to just accept complex code. Now, why did I talk about individual pieces instead of the complexity of the entire system? Well, one of the reasons is that the average software system is so complex that no human being could possibly hold it in their mind at once. You think of something like fundamentally feature-wise simple like Twitter, which is, a system where, you just post 140 characters and then people can see them. And I can guarantee you, I haven't seen their code base, but I'm sure that it's so enormously complex that no human being could possibly hold it in their mind at once. So there's, any system that does anything decent is going to be too complex for you to understand as a whole. As a result, our only hope is to be able to understand the pieces when we look at them. And that's actually okay, because in a well-designed system, we are only modifying pieces of the system. any time that the system requires us to do a modification beyond our level of understanding, there is a complexity that is too high. So this is somewhat self-proving, but also a fairly useful guideline for, okay, this is too complex, and the way that I resolve this complexity is I break it out into a simpler piece. And once you have pieces that can be understood, then you go, okay, now it's simple. That's a pretty reasonable approximation for simple. But the other reason that I talk about individual pieces is because, like I said when I was talking about the code reviewer with the patches, is that complexity compounds on itself. It builds on itself. You know, you introduce change A, and that adds a certain maintenance cost to the entire system, and then you introduce change B, and that introduces a certain maintenance cost to the entire system. So what we need to do is we need to, you know, make sure that every change, every piece individually is introducing as little complexity into the rest of the system as possible by itself being fairly simple. You know, there can be some amount of complexity on the inside of it, but you know, as long as the outside of it, its interfaces are simple, then we're good, and then we can go inside of it, and if it gets too complex on the inside, we can refactor it on the inside, and it's not adding a ton of complexity to the rest of the system. It's always going to add some complexity to the rest of the system. You can't, you know, just like I said, there's no black and white, there's no absolute right or wrong decisions in software design. There's also no change that introduces no complexity. All changes introduce, all new features, at least, introduce some level of complexity. Obviously, hopefully, if you're refactoring, that introduces simplicity and reduces complexity. So that's the law of simplicity, just like everything else. There's a lot more to know about it. And I'm happy to come talk to, you know, you guys, anybody in person about it, or you can read the book. And our last law is what is called the law of testing. There's, of course, this famous quote from Donald Knuth that says, "Beware of bugs in the above code. I've only proved it correct. I have not actually tried to run it." Basically, this law says that the degree to which you know how your software behaves is the degree to which you have tested it. And some people have argued, well, I could run a prover over my system, and that would tell me what it's doing without having to run it. And that's true, but what you've really done is you have actually tested it. You've tested it against an abstract universe, against a computer that doesn't actually exist. So, you know, you don't. So that does tell you quite a bit, and that is useful information, but it's still a form of testing. Obviously, that's not the traditional word used for it, but it's the way that I think about it in sort of a framework of knowledge. And what this law tells you is a couple of things. So a lot of people know, okay, unless you've tested it, you don't know if it works. You know, everybody has written a couple hundred lines of code and then run them, and then they doesn't do what they expect. I mean, in fact, that's the most of the time. I've been writing software for almost 20 years. And fixing computers for longer than that. And almost never does a change do what I expect it to immediately. I've always made some little mistake, and then I have to fix it. But there's a question here. And the question is, when we say it works, what does that mean? What does works mean? Well, works really means that it behaves as you intended it to. And what a test is really telling you is it's telling you that the behavior you expected is the behavior that a piece of software does. And sometimes when you're having a little difficulty thinking about how to test something, instead of thinking about, because you can't think what does works mean, that's your problem. And that can sort of help you realize, okay, now I have to think about what does works mean for this piece of software. Works means X, Y, and Z. Okay, well, so I just need to write a test that makes sure that X, Y, and Z happens. And that pretty much also tells us what we need to test. In addition to a couple of other useful points that I make about it in the book. So now people always ask me, okay, you told us these things, but what do we actually do with them? Like we told us these things, and some people are like, okay, not only did you tell us these things, but I already knew these things. So what have I gained by highlighting these particular items. So I'm going to take a couple of examples of real-world software development or situations that people get into and talk through them and show how we would apply these things. So let's answer a question, okay? And a question that comes up a lot when I'm talking to people who are writing tests is, should I mock out some class in a test? Now, for those who don't know, a mock or a fake is something that looks like the real class, but it isn't. It has some sort of like deterministic behavior, or it always returns the same number, for some function or something like that. And there's sort of this religion that's grown up around mocking and testing, and so people have a hard time making decisions about it because there's conflicting religions. So I try to, whenever this discussion comes up, I try to bring a little sanity into it by using these laws and rules. So the first thing we can look at is that the degree to which your software behaves is the degree to which you have tested it. Okay, so one of the important things here is that if you are testing a mock, you are not testing your software. You only know how the software behaves with that mock. Now, this doesn't eliminate the whole use of mocks, right? But it sort of limits their use, right? You have to structure your tests in such a way that ultimately you do test everything in the system, and you know how the system actually behaves, not how a fake system that you wrote for the tests behaves, because that's not what you want to test. The second point is the longer your program exists, the more probable it is that any piece of it will have to change. So how is this relevant? Well, this is relevant because mocks also have to be maintained. And a lot of the time they have to be kept in sync with the original class. You are adding maintenance effort by adding a mock. You are also adding the potential for future defects. This happens all the time where somebody modifies a class and then doesn't modify its corresponding mock. And one of the worst things that can happen in this case is that you have tests that give you false positives because they are testing a system that is not yours. However, the purpose of software is to help people. Who are tests supposed to help? Well, tests are supposed to help developers. What makes tests helpful? One, that they are deterministic. If a test sometimes fails and sometimes passes, it is not a useful test because it gives you no knowledge. What you want is you want a decision. You want information. You want knowledge, certainty out of a test. A test that is sometimes yes and sometimes no is a maybe, which is not certainty, which is not knowledge. And then secondly, the tests are usually the more helpful as they become faster. Tests that can be run in 10 seconds for an entire test suite will be run over and over and over by the developer as they are developing, which is very, very helpful. Whereas tests that take an hour or 2 hours to run are considerably less helpful, and they will usually only be run by the continuous integration system, assuming you even have one. They may never be run by developers, and thus they are helping nobody. So this tells us basically, and at least in this line of reasoning, and there may be other lines of reasoning, but I think this is a fairly clear one, that the purpose of mocks should be to make your code deterministic, your tests deterministic, or to make them faster. And that is worth the additional complexity and the additional the additional work required in your tests. But you also have to remember to make sure that you are still ultimately testing whatever you mocked out somewhere else also. Okay, another question. So, people often wonder, should I program defensively? So defensive programming is like, you check all your input, you make sure that nobody can, or, like you clone all your input variables so you're sure that you're not modifying anything out, that you were passed in. All kinds of things, right? So we can look at this and we can say the ease of maintenance of any piece of software is proportional to the simplicity of its individual pieces, right? So we know that, and adding code and adding adding all this defense is adding complexity. So you're adding an ease of maintenance, and that's making your changes and your work less desirable, right? You look at the equation of software design below. You're adding effort of maintenance, and that's making things worse. So you can see that in a general sense, defensive programming is something that you may not be desirable, particularly when it adds complexity. However, there's another side to this, which is that there are unforeseeable consequences. Okay, so but this is a blade that cuts both ways. This unforeseeable consequences in this situation of defensive programming. One of them is that you may be writing a piece of code internal to your program, and when you are programming defensively, you are making some assumption about the future. You are predicting that you will get bad input, and it may be impossible for you to get bad input. So there's no reason for you to check it. On the other hand, you might be writing a public API. And this public API, anything could happen. You don't know what kind of input you could get. You don't know what people could possibly give you. And in that situation, it's worth the complexity trade-off, because the thing you know is that you don't know in that situation. Whereas in an internal piece of software, you know what input you're getting. So you don't have to worry about it. So that pretty canonically answers the question of should we program defensively, and I've never seen a better or another argument that works better than that, or gives you a better set of guidelines than that. So those are just two examples. There's lots of other ways to use this, but hopefully this gives you an idea of sort of how you use these to reason through problems. And that brings us to the Q&A. Also, I just wanted to point out that I have a blog where I talk about these sorts of things and software design issues and a lot of things that aren't in the book. So the blog is definitely a supplemental to the book. I am available for speaking engagements. I speak at conferences. I do a lot of corporate speaking engagements. I talk on a lot of different topics. In addition to this one, this is usually similar to my introductory talk, but I do a lot more detail in person. And I can also talk about code reviews. I can do all kinds of stuff. And of course, I wrote a book. And the book talks about where complexity comes from. It gives you a checklist that tells you when you should rewrite. It gives you a checklist that tells you whether or not you should reinvent the wheel for a particular piece of software. And there's a ton of real-world examples. I also have another webcast coming up on December 12th at 1 p.m. Pacific, where I'm going to talk about the 4 components of software, which is basically a method of analysis for all pieces of software that helps you make software design decisions. And with that, I would like to turn it over to the Q&A.
Great webcast, Max. Thank you so much. Folks, as you heard, we are at Q&A now. We do have one question that has come in, Max, but we'd like to let people know, please, if you haven't opened your group chat widget, click it, open it now, type your question in for Max, send it in so he can answer it while he's with us.
All righty. So let's see. So one of the questions here is, how many decoupling strategies are presented in your book? That's an excellent question. So what I felt like the world is full of books about decoupling strategies. And the world is full of books about a design pattern. And what the world is not full of is the world is not full of simple summaries of the overarching principles. Books that you could give to your manager or to a new programmer to help them understand why decisions are being made. There's a lot of highly, highly technical material that is great for people who are trying to figure out, learn things. And that's one of the problems, is that people often give you like a book full of design patterns, or a book about refactoring with a little bit of why and a whole lot of how. And I wanted to give people a book with a lot of why and leave a lot of the how to books that already existed, because I felt I didn't need to write those books. Okay. So next question is, can you speak to standards and how that accomplishes the issues you raised here, specifically how WebKit et al. Helps or hurts? Yeah, sure. So standards, so hopefully what standards do is they create consistency. And consistency, as I mentioned in the book, is an important part of simplicity. And even in situations where you can't get to simplicity, if you have consistency, at least people will eventually learn it. Now, there's a couple of issues with standards. One of them is that you can't write them inflexibly, because standards will change just like software changes, because the environment changes. You have to keep them up to date, and you have to write them in a way that allows for extensions and changes. And it's also possible to write standards that are themselves much too complex, and then you are sort of making a consistent complexity throughout the world. I wrote a blog post about positioning things in CSS as an example, which I think is an unfortunate system that we all now have to deal with because it's the standard. I guess the next question is, so WebKit, the rest of this is like WebKit, so everybody is sort of now porting WebKit, and everybody's using WebKit, and I think that's another question of sort of a slightly separate question of, what's the advantage to having all this open source software that we all share? Well, I would hope that the advantage is a lowered effort of maintenance to accomplish more value, or a lowered effort of implementation. That would ideally be, one of the advantages of standards should hopefully be that people can write libraries, and then you can reuse these libraries. And I think that you can sort of judge the success of the standard by how well people have been able to do that. If you can't write a library that everybody can actually use for your standard, then maybe there is something wrong with your standard. Okay, let's see if there's another question. Okay, so next question. Can your scientific formulae be used to predict the ease of maintainability of a given module or piece of code? Sometimes one needs to provide facts and figures to convince peers to follow a given strategy. Yes, so this is a sort of a timeless question in the field that I work in, which is the sort of the field of code quality, or the study of software engineering, and it's how do you get metrics for code complexity? There are metrics for code complexity. Most of them are bogus, and some of them are somewhat useful. You can look up this thing called cyclomatic complexity if you want, and it gives you some hints. You can try to write tools that detect code duplication if you want. I haven't seen really great tools that do that yet. I'll try to give you counts out of them or metrics. What I tell people is that there's only one valid metric of complexity that I'm aware of, and that is how long does it take a developer to understand this piece of code and use it correctly? If they use it incorrectly, the time is basically infinite, or until they realize their mistake and fix it. You could possibly judge this by velocity, but I guess the question, and so really the overall question is, how do you convince your manager that refactoring is worthwhile? And I get this question a lot. There's a couple of ways. The best way is to get them to read my book. That is one of the reasons why I wrote the book. It's very short. It's like 75 pages long. They can read it in a day or two. And it will explain to them why you want to do what you want to do. And many non-technical people who have read my book have been really happy with it and have suddenly had a much better rapport with their engineers. But another option is to not ask for permission. This is often what I do. People say, how long is it going to take to write this feature? And I say it's going to take 2 weeks. And the reason it's going to, and I don't tell them that the reason it's going to take 2 weeks is because I need to spend the first week fixing your really complex system and refactoring it to make it simpler. And the fact of the matter is it really is going to take that long because otherwise I'm going to be adding complexity to the system and adding a maintenance burden in the future, which is going to make the system even harder to maintain and longer to fix. But if one wants facts and figures, sometimes what is helpful is finding other projects that have done refactoring. And there are various studies. I know of studies that are internal to Google that I unfortunately cannot share with you yet. I would like to get some permission to talk about those more broadly. But I can assure you that these things work and that they definitely increase velocity. And that they, yeah, by reducing maintenance complexity. Okay. So how to test complex scenario with network service interaction and mock-up users could fail. Yes. Okay. So the question here is basically, I have something non-deterministic on the other end of the line, like a network interaction, and how do I test it? So I approach this from various different ways. If the network service is fast, and I'm pretty guaranteed that it's going to be fast, sometimes I just don't mock it out. It really depends upon the team that I'm working on and the environment and the system that's running our tests and how fast they need to be. So a lot of the time I just actually talk to the network service during my tests. And I try to make sure that, and that's also nice because it tells me that the network service is returning what I expect it to return. If I can't do that, then I write 2 separate tests. One test that mocks everything out, and then another test that just makes sure that and sometimes this test is run separately, right? So people sort of refer to this as the difference between an end-to-end or integration test and then a unit test, which is sort of the unit test is a smaller test, the faster test, and the integration test is the slower test. And really that's just sort of a scale, and you can think of them as small tests or fast tests and then slow tests or large tests. And so sometimes what I do is I write a series of unit tests that use the mocks, and then a separate integration test that runs in a separate test suite that makes sure that the network service is returning what I expect it to return. Or another option, depending on your test framework, is to have a switch that you can flip. And when you flip this switch, it talks to the real network service, or it talks to the mock. And then you run the one that talks to the network service like once a day or something, or every couple hours instead of after every commit. Okay. So I got this question that says standards like MISRA. I'm unfortunately not familiar with that standard, so I can't speak to that. But if you clarify the question, then I would be happy to address it. So next question. Should you assume the infallibility of a given framework, such as WebKit, or can one devise a defensive strategy to cope with possible bugs introduced by third parties? Interesting. So usually I assume the infallibility of external code unless I have had it significantly demonstrated to me otherwise, or if I'm in a situation where I don't like where an error with it would take down the site. So or would do something really, 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 really bad. And in that case, if I do get defensive about it, I try to do it at the very highest level, right? At like one level where it's, and like not on every single call. Like I don't want to check the return values of every single call. What I want to do is I just want to put like some exception handler at the highest level just to make sure that everything doesn't crash. Otherwise, I'd like to fix the third-party system. And if I can't fix the third-party system and it's really consistently bad, then ideally I'd get another one. Now, I have worked with third-party systems that are really consistently bad and that I can't get another one of because it's the platform that I'm working on. And in that case, I wait until it demonstrates some particular problem, and only then do I work around the problem. So I'm never prematurely defensive. The next question is, keeping in mind the future maintainability effort, in the cases when you need mocks in order to test your system, do you go for mocking frameworks or for manually created mocks, and why? That's a good question. I usually do manually created mocks. I think it depends upon the size of your system. You know, like once you get up to like a couple hundred, like 100,000 lines of code, and you have like this enormous amount of tests, all of a sudden a mocking framework, if you have a lot of mocks, is really useful. Like if your system is just super heavily network dependent upon a zillion different network services, or does like just a ton of like asynchronous I/O or something, you know, something non-deterministic, then a mocking framework comes in handy. And I'm particularly, if you're at a company and that company has millions of lines of code, then standardizing on some mocking framework, probably reduces implementation effort of tests enough over the company to justify everybody having to learn it and, sort of fit it into their systems. But barring a good reason to use a mocking framework, I often just write manually created mocks. In fact, a lot of the time what I do is I just subclass my real classes, and I mock out the part that does I/O. With, I override the function or something. Okay. Next question. What's your take on documenting software design and discussing/communicating design decisions with non-technical people? So I definitely don't think that non-technical people should be involved in technical decisions. And companies that do that are bound for hard times. But I think that what I think there's value in is there's value in a couple of things. One, having like little readmes or documents that explain the structure of the system to people who are new to it, because that's really helpful. Like people can tell you, oh, just go read the source, and that's fine if you just want to understand how one class works or how one function works, but it's not necessarily always that helpful if you want to understand how the entire system works. And if you're totally undistributed and everybody's in the same room, then you can ask other people. But that's not even that great, because what if the person who knows leaves the team, right? So I support writing up general discussion, writing up a general idea of how the design of the system works. And I also particularly support explaining why you made the decisions you did, because that information is not encoded in the code. And if future maintainers don't know why you made a decision, they will incorrectly reverse it, because they will look at the complexity that you added to handle some important situation, and they will just get rid of it. They'll just be like, I don't know what this is. This looks like stupid garbage. I'm going to delete it. So I think that's valuable. Now, but as far as discussing or communicating design questions with non-technical people, I usually work in situations where I don't have to do that, and I feel like having non-technical people demand explanations of technical things is, I guess I have worked with that. I ran a business, and my business partner was not a technical person, but mostly I think as long as you give sort of a vague, high-level overview of why things are going to take the amount of time they're going to take, people are usually pretty happy without you having to sort of dive into the nitty-gritty specifics of it. Let's see if there's more questions here. Okay, next. How to obtain funding for redesigning when I am the one who designed the system 3 months ago? Yeah. So that is a tough situation, right? How do you convince people? Well, first of all, you should hopefully be able to demonstrate that you are somehow now a better designer than you were the first time, and that that as you refactor the system, and hopefully not just rewrite it from the ground up, there is actually going to be value in that. And another option is to see, now hopefully you're not rewriting the system from the ground up. Because if you are, there's a lot of chance that you're going to redesign a system that's just not good in different ways. But another option is to just refactor as you go and not ask for funding, and just start to tell people that it's taking a little bit longer to write features. And sometimes you can't do like mass refactorings because of your time constraints, but you can start to do little cleanups. You write some change, and as part of that change you fix some variable names. Or as part of that change, there's like a 100-line method, and you split it out into a couple of 20-line methods, and then just call all of those, right? Like, you can start to do little cleanups as you go, and eventually those little cleanups will help you build velocity, and you will be able to do larger cleanups with less slowdown. So at the worst, even if you can't get funding for it, or you can't get time to do it, then you can still accomplish a redesign of the system more incrementally. And of course, it can also help to try to have your manager either A, read my book, or B, look up the concept of technical debt on the internet, and tell them like all software projects should have some time to fix technical debt, which isn't really true, actually. All software projects should theoretically be refactoring as they go and not build up a ton of technical debt. But in reality, all software projects existing in the world today tend to need some time to clean up technical debt. Okay. MISRA is a standard which is style and rule related. How you should write your code, danger structures and things must be avoided. Oh yes, like some of those government standards. Okay. So this brings us to a larger question of coding standards. Coding standards. So ideally, the purpose of coding standards is to bring consistency to a system. The problem with coding standards is that if there are rules that don't actually apply in every situation, but you force people to apply them in every situation, then you are adding code complexity to their lives. If you prevent them from using some feature that in their particular situation is totally fine, and they have to re-implement that feature, like using their own code, or they have to make something way more complex because they can't use that feature, that aspect of the standard is harming you. The important thing with standards is to allow, with standards like that, with coding standards, is to allow people to use their judgment for all things that aren't purely consistency decisions. Like you cannot use your judgment about how many spaces to indent. That has to be decided by an authority. But things like you should or shouldn't use this particular piece of software or this particular coding construct, that is something that you should possibly allow a little bit of judgment on, or come up with a series of exceptions, or allow people to propose exceptions to your standard. So that's my viewpoint on that one. Question. Okay. Do you see the trend of modularizing code continuing, increasing in the future, and meaning in the future code will become separated to increase flexibility? Sorry, like CSS and HTML are now separate. I mean, I would hope that people would modularize code intelligently, and even in these conceptual concepts. I mean, I like the idea that HTML is just for describing the structure of your document, and CSS is for presentation. And I think people would like this even more if CSS were a better presentation language. I think people's problem is that CSS is a very difficult presentation language, and that HTML is actually a pretty good structural language. But I would hope that in general, yeah, that because sort of the ideal of software development is that we as a society of software developers are building up a framework that makes the effort of implementation and the effort of maintenance for all software in the world easier. That as time goes on, we eventually collect this beautiful collection of libraries that become more and more and more perfect as we work on them more and more and more and more. And this isn't the case right now. People keep designing broken systems and then patching them and patching them and patching them and patching them, and until they become basically more and more and more and more broken, and have all these weird workarounds and all these strange complexities. And instead of becoming better and better and better and better, our systems become worse and worse and worse and worse. and there's some amount of progress. Like you can see, like jQuery changed the way that people did web development to a large degree. Because all of a sudden it gave them tools. It made the effort of implementation easier. It made the effort of maintenance easier. And I think that was a great win for the Internet. But not all frameworks do this. and not all code development does this in the world. So, hopefully what I'd like to hope is that the trend of good modularization continues, and the trend of bad modularization or just bad software development dies down. Alrighty, I think that is all of our questions.
I'm not seeing any additional questions. So with that, Max, is there anything you'd like to leave the audience with as we close out?
I guess thank you everybody for coming. If you have any other questions, or if you'd like to get in touch with me, there's usually some contact method on my website.
Perfect. With that, Max, thank you so much for an outstanding webcast today, for sharing all your knowledge and expertise with us. Folks that attended, thank you for attending today's webcast. We hope you benefited from it. And just a quick comment, Max, as I'm looking through the group chat, lots of good conversations going on. So it seems people really did get a lot out of your event today and did enjoy it. So again, thank you folks for attending and Max for presenting. Folks, in case you didn't know, Max's book is the O'Reilly Deal of the Day today. And what that means for you is you can get it today at a really great price. Code Simplicity is the book. Visit O'Reilly.com. Look on the right-hand side of the homepage. You can't miss it. It's right there. Get it today. Save yourself some money. And if you like what you heard Max talk about today, the book has so much more in it that will really help you with your day-to-day. Again, we thank you, Max. Thank you, everyone. And we hope to see you at the next webcast on December 12th. This will conclude today's webcast. Goodbye, everybody.